Hello friends, welcome to CEC live lectures. Dear friends, in this session we are going to talk on UV visible spectroscopy. We already had one session on the following topic, and continuing further we are going to give you more of knowledge on UV visible spectroscopy. Friends, for the discussion on the topic we have with us in our studios Professor Sanjeev Kumar. Professor Sanjeev Kumar is from School of Sciences, Indira Gandhi National Open University. Friends, if you wish to ask questions from Professor Sanjeev Kumar, then do call us through our toll-free number. Our number is 1800110430. Now, I would like to welcome our guest, Professor Sanjeev Kumar, once again, and would request him to explain us in detail about UV visible spectroscopy. Hello, sir.
Thank you so much. Okay, friends. You would recall that in the previous session, we introduced the concept of UV visible spectroscopy as one of the oldest spectroscopic methods. You remember that it is based on the interaction of electromagnetic radiation in the UV visible range, that is from about 200 nanometers to 800 nanometers with the molecules. And this actually leads to the generation of a spectrum. And further we talked about that there are a number of factors that affect the nature of spectrum, and the factors being conjugation, solvent and substituents, etc. Of these, we talked about one of the factors. We started talking about conjugation. In this session, we will continue from there, continue with the discussion on the effect of conjugation on the spectrum, and then thereafter talk about other topics. And towards the end, we will try to bring in Woodward-Fisher rules, which basically try to give an idea about how to use these factors to predict the lambda max or the wavelength maximum for a given UV visible spectrum. Okay, let's make a beginning. And let's recall that when we talked about effect of conjugation, we talked about effect of conjugation in two kinds of species there. First, we talked about in case of alkenes. I'll quickly recall this for you. Remember that in case of alkenes, what happens is, suppose I start with ethylene, there are only two energy levels there, and then this delta E is such that the wavelength maximum comes out to be about 171 nanometers, which is outside the UV visible range. When it comes to butadiene, it comes at 217, because in this case the energy difference between the HOMO, that is highest occupied molecular orbital, and lowest unoccupied molecular orbital, that becomes lesser. When the extension of conjugation takes further, when we have got a hexatriene, we find that this delta E value becomes still smaller. That means as more and more conjugation comes in, the delta E value for the transition of HOMO to LUMO, that decreases. And since the delta E decreases, the lambda max increases. That's one general observation we had in case of alkenes. Thereafter, we talked about the effect of conjugation in carbonyl compounds. Here again, we found that there are two kinds of possibilities. There are two transitions in case of carbonyl compounds. One is N to pi star, second is pi to pi star. And in both the cases, when the conjugation, this is acetone, and we got two transitions there, and then there are 274 and 195 nanometer are the positions where the spectra comes there. But when there is a conjugation with one double bond over there, we find that both of these signals move to higher wavelengths over there. So that is the effect of conjugation we talked about here. Okay, let's continue from here and see that what will happen if you've got two unconjugated double bonds. What happens in such a case? Let's take an example here. Say I've got pent1-ene. This is only a single double bond over there. It absorbs at what 176 nanometers outside the range of UV. And if I got pent1,3-diene, it is a conjugated system over there, and we find that the lambda max becomes 223. It's a very significant change from here to here. As against that, if I have got this molecule, that is pent1,4-diene, wherein there are two double bonds there, but the two are not conjugated, we find that the lambda max happens to be just 178. That means there is no significant change if the two double bonds are not conjugated. That means they actually act as independent of each other. There is no conjugation, so there is no lowering of energies, and there is no decrease in the delta E values there, and consequently there is no change in the lambda max. That's a very, very significant thing. That is, conjugation is a very, very crucial phenomenon for the UV visible spectrum to be observed firstly, and secondly to get affected. We'll talk more about it as we proceed further. Now let's just see one more aspect of it here, that is the effect of conjugation happens to be additive. I've put down a series of molecules over there. There is just a double bond over there, 171 nanometers. There are two of them, that is butadiene, we got 270 nanometers. Hexatriene, octatetraene, and so on and so forth. As the more and more conjugation comes in over there, we find that lambda max goes on moving there. And on an average, we find that addition of one conjugate double bond increases the lambda max by about 30 to 40 nanometers. That's a very significant change in the lambda max value, and accordingly the molecule's nature will change, the behavior will change, the spectrum will change, the color also will change. We'll come to that. Okay, now let me take one example over there. We all know that the tomatoes are red, and if you look at the spectrum of tomato, that looks something like this. And there are two kinds of signals over there, one in the visible range, UV range over there, and then there are three signals in the visible range there, and these are the three signals over there which are responsible for the red color of tomato. And the pigment which is responsible for this red color happens to be lycopene. In case of lycopene, we find that there are as many as about 11 double bonds over there which are conjugated. That is why the lambda max comes out to be around 471 nanometers and so on and so forth. That means there are two things over there. One, there are number of double bonds over there which are conjugated, and secondly there are certain substituents over there which also affect the lambda max. We will talk about this little later from here. That is one example. Second example happens to be, say in case of pink carrot over there, we find here again the spectrum looks something like this, and in this case the beta carotene, the pigment which is responsible for this color here, this also has incidentally about 11 double bonds over there which are conjugated, and also there are substituents which are different from what we had in the previous case over there. Accordingly, the spectrum is different, and here again the important thing which I want to bring home is that it is this region here, that is around 455 nanometers, that absorption is the one which is responsible for the color of this particular species over there. Okay, so we see that conjugation is very crucial. Let's try to establish this further here, and for that we'll come to that a little later, but before that let's talk about the effect of solvent here, because we said there are three things which primarily affect the nature of spectrum. One is conjugation, which we discussed in detail, and second happens to be solvent, and then we talk about the substituents also. As against the solvent effect goes there, the effect of solvent on the UV visible spectrum, there are two things we have to keep in mind here. That is, the effect will depend on two things. One, what is the nature of solvent, whether the solvent happens to be polar or non-polar. That is one bit. And secondly also, it will depend on that this actually affects by changing the energies of this thing, energies of the levels involved in the transitions there. And second thing is that since it is changing the energies of the levels which are involved in the transition, as a consequence it is the position of the signal which matters there. Because you remember that when we talked about the characteristics of the spectrum, there are three things there. There is a position, there is intensity, and there is width. So primarily when we talk about a solvent effect, it is more of the position effect there. That means the position of the lambda max or the signal where it comes, that moves either to a lower wavelength or to a higher wavelength there. We'll come to that. Okay. Now then we said that the effect of solvent will depend on the nature of solvent there. So suppose I start with the effect of polar solvents. If I look at the polar solvents, we find that the polar solvents actually they alter the energies of the initial and the final energy levels differently due to difference in their interaction with them. Let's understand this. What basically is happening here? What basically is happening is we have a given level here, say E1. We have a level E2. There is a transition taking place from level 1 to 2. Okay. Now, if this is happening in a given solvent here, if I change the solvent, bring in some polar solvent there, that polar solvent will interact with both the energy levels there, so E1 and E2, and change their energies. That is one bit. And secondly, the change happens to be different for the two levels over there. As a consequence, what happens is that this delta E value changes, and that leads to change in the nature of spectrum. That means the position of spectrum will change there. And what you find is that the effect of polar solvent actually depends further on the type of transition. That's very, very interesting, because we know that typically the kind of transitions we observe in UV visible spectroscopy happen to be, say, N to pi star and pi to pi star. They are the most important ones there. And what happens is, if I add a polar solvent that interacts with the molecules there in such a fashion that the nature of interaction between the two kind of transitions, N to pi star and pi to pi star, they happen to be different. As a consequence, the two transitions are affected in a different way, to different extents over there. And what we conclude from here is that is the spectrum in polar solvents may vary significantly from that in the non-polar solvent. That means we have a system which I take a spectrum in the non-polar solvent, I observe something, add polar solvent to that, I find there is a significant change in the spectrum over there, primarily in terms of the position there. Okay, let's talk about the effect of polar solvents depending on what kind of transition we're talking about. Let's begin with the effect of polar solvents on pi to pi star transition. If I'm talking about pi to pi star transition, let's see what happens here. What happens is, that is, we have a transition, we just said there's a lambda level 1 to level 2, that's the ground state to excited state. This polar solvent actually interacts with both these energy levels, that is the ground state as well as excited state, but it interacts in a differential way. That is, the decrease in the energy of excited state is far greater than that in the ground state. Let's understand this by this diagram over here. So this is the starting point here. This is in the non-polar system there. So you have this pi star. This is the transition I'm talking about over there. So it has certain delta E value over here. But when I add polar solvent to that, what happens is the energy of this pi level decreases by a certain amount there. Delta pi star also decreases. But this decrease happens to be much larger than this decrease. As a consequence, what happens is that this delta E value, we can call it as delta E prime, this happens to be less than delta E. Since the delta E value decreases, we find that there is a shift to a higher wavelength in case of the pi to pi star transition. That means the pi to pi star transition, which is observed at a given level, a given wavelength, shifts to a higher wavelength over there. Okay, that is about effect of polar solvent on pi to pi star transition. Let's see if it happens to be n to pi star transition, then what happens there. In case of n to pi star transition, actually the polar solvent decreases the energies of ground as well as excited state, and the cause happens to be hydrogen bonding there. And what happens is, it is just the reverse of what we observed in case of the effect on pi to pi star transition there. And what we see is, that is, the decrease in energy of the ground state happens to be more now than the excited state. In the previous case, the excited state was stabilized more than the ground state here. It is just the reverse of it there. So what happens is, to begin with, I have this transition here. Say this is n level, n to pi star. Then this happens to be the delta E value there. But when you bring in the solvent, the polar solvent here, that this n level stabilizes to a great extent here because of hydrogen bonding there. This also stabilizes, but to a lesser extent. And as a net result of this delta E value actually becomes very large. It becomes larger, that means now the wavelength will go to a lower value there. That means there will be decrease in the wavelength for this particular transition over there. So we can see that the polar solvent affects the transitions pi to pi star and n to pi star in a different way. In one case, the lambda max shifts to higher wavelength. In the second case, it shifts the lower wavelength there. Okay, let's go further and see, just about take an example over there. So this is a spectrum of a given molecule here, say acetone. It was taken in hexane to begin with, and then if I put water to that, what happens is that this is what's happening. That means we have lambda max somewhere here that shifts to a lower wavelength there. So that actually indicates that we are talking about the effect of solvent over here. Okay, let's go further and see that what will happen if I try to bring in non-polar solvents there. Non-polar solvents actually generally do not interact much with the solute molecules in the ground state or either in the excited state, and as a consequence they do not really cause significant changes over there. And the absorption spectra in these solvents generally is similar to the ones which are observed in case of pure gaseous state of the compound there. What does it mean is the following. That means if I have a compound and if I can measure the spectrum of that compound in the vapor phase or in the gaseous phase, I get certain spectra there, and take the same molecule or same compound into a non-polar solvent and take the spectrum, it will be something similar to what we had in case of the vapor phase there. That means there is no significant effect of the non-polar solvent over there. So you can see that how important it is. That is, we will see the significance of this when we move a little further towards the end of the session here, when we try to actually work out the wavelength maxima for a given kind of molecules over there on the basis of the structure there. Okay, let's go further. Let's go further and bring in one more thing, because to move further we need to recall a few things there, and that is what is called as the Chromatophore Auxochrome theory, because these terms we are going to use in the UV visible spectroscopy very often there. So you will remember that in your earlier classes you learnt about color, and we know that when the white light falls on a given object, part of it gets absorbed and rest gets reflected there, and then this light which has got reflected adds together and falls on our eyes and is perceived as color. And color primarily happens to be a psychological sensation. When the light of a certain wavelength in the visible range falls on the retina of the eye, because what basically happens is when the light of a given range out of this visible range falls on our retina, there is some kind of a transition. There are a lot of molecules there, the proteins are there, the protein conformation changes, that leads to generation of some kind of a signal there, that is actually goes to our brain, and then we perceive some kind of a color there. Okay, so I'm sure that we have learned about that in the earlier classes there. But what's important here is that how do I relate color with the constitution? You had learned about this theory in your earlier classes. I just tried to quickly recall for you. There are two concepts we have to understand here. One is what's called as a chromophore, and second is called as auxochrome. Chromophore is that part of the molecule which is responsible for absorbing the radiation in the visible range there. Say I've taken an example of a dispersed orange tree. It's a dye, and in this dye, this part of the molecule there, if you just start from here, so this is a double bond there, single, double, single, double, single, double, single, double, and so on and so forth. This is an extended conjugation over there. So it is this part, the extended conjugation over there, which is responsible for the molecule to absorb in the visible range there. So this part which absorbs radiation in the visible range is called as chromophore. Chromophore. Chromo means color, phore means bearing. So it is a group of the molecule which is color bearing. So chromophore basically is a color bearing group of the molecule there. So that is one thing, because if a given molecule doesn't have a chromophore, it will not absorb, as simple as that. So that is one of the very simple thing to understand here, that for a molecule to be colored, it must have a chromophore, which essentially is a conjugated system over there. We saw earlier two examples over there. Say in case of Lycopene, there was a long chromophore over there, about 11 double bonds which are conjugated there. Okay, and the second thing we have to understand here is what's called as auxochrome. Auxochromes are certain groups which are attached to the chromophore in the molecule, and they affect the lambda max value, and the lambda max either increases or decreases, or the intensity changes, it decreases or increases over there. Essentially, in a way, they basically modify the chromophore there. And in this example again, we find that these two, the NH2 here and NO2 over here, they happen to be the auxochromes there. So we've seen something is encircled in the red one here is the chromophore, and then these two groups happen to be the auxochromes. So they are the ones which modify the chromophore, and as a consequence, the nature of spectrum changes there. Nowadays, even this term auxochrome is used less often there, because they actually has become more of a modifier of the chromophore over there. Okay, let's go further and take one more example here, just to establish this part over there. Say benzene. Benzene absorbs at 255 nanometers. There are 3 double bonds over here. But if you introduce an auxochrome like OH here, you find it becomes phenol and absorbs at 270 nanometers. And aniline absorbs at 280 nanometers. Essentially, I'm just trying to demonstrate the effect of auxochromes onto the basic chromophore. This is a basic chromophore, and these are 2 auxochromes, and we see that lambda max has changed over there. And actually, the auxochromes work in the way that is the lone pairs of the auxochromes, they interact with the main chromophore and change the lambda max value. Okay, and we find that this lone pairs are very, very crucial here. Let's try to understand with 2 more examples over here. Say again the same example here. So you have benzene. Benzene, if you introduce the chromophore auxochrome over there, that is OH group here, it becomes phenol. Lambda max shifts from 255 to 270 nanometers. But to this, if I just ionize this, suppose this phenol gets ionized to phenoxide here, what you find is that there is addition of one more lone pair there. There are 2 lone pairs there, now there are 3. And then we find that lambda max goes from 270 to 287 nanometers. That is, addition of lone pair on the auxochrome by ionization increases lambda max. Another example we see start with benzene, we have got aniline 270 nanometers there, and if I just do protonation of this, add little acid to that, this will become anilinium ion. In anilinium ion, we find the lambda max becomes 254. Just this effect which had come because of auxochrome is lost because this lone pair is lost. So we can appreciate that this lone pair of the auxochromes are very crucial in terms of affecting the nature of chromophore there. Okay, let's move further and see that how do we kind of summarize the effect of auxochromes, because auxochromes can affect in variety of ways there. And if this so happens, that is, this is a lambda max position. If lambda max goes to higher wavelength, we say it is a bathochromic shift. It goes to lower side, it becomes hypsochromic. If the intensity increases, which happens in some cases there, it is called a hyperchromic effect. And if intensity decreases, it is called as hyperchromic effect. So there are typical things which will be coming often, very often, when you talk about UV visible spectroscopy there. Okay, so having recalled this, because why did we talk about it? Because we needed to know about the concept of chromophore there, because we want to bring in the effect of substituents there. Before we wind up for this session, we want to bring in the effect of substituents there. Basically what happens, you have a molecule and there are certain kind of a chromophore by which the molecule is absorbing in the UV visible range there. Now there are certain substituents there. They also affect the energy levels there, and as a consequence they change the position of the lambda max over there. And I'll just give you an example there. In this case, we find that the methyl group, which is one of typical a common substituent over there, that actually can affect the thing by affect the chromophore by hyperconjugation. I'm sure that you learned about hyperconjugation earlier in your classes there. That is, you've got this as the chromophore there, and this is the methyl group over there. I just shown only one of this kind of orbitals over there. So this is basically is called as no bond resonance there. Hyperconjugation is no bond resonance, and because of hyperconjugation we find that the lambda max shifts there. That means the substituents affect by introducing some kind of a conjugative effect, but not as significant as the conjugation of double bonds over there. It is much weaker than the conjugation effect what we observed in the extension of conjugation and so on and so forth there. Okay, before we wind up, let's quickly see one more thing over there, that is just to establish this part over there, that is pi to pi star transition in butadiene is sensitive to the substituents there. Let's take some examples over there. This is butadiene, and we know that for butadiene the lambda max happens to be 217 nanometers there. Okay, and if you look at these molecules there, so in this case butadiene, there is one substituent over there, so this becomes 220 nanometers. Two substituents there, 227 nanometers there, and this is 223, 232, and so on and so forth. What you find is that depending on, we have the basic chromophore there, and then the certain substituents are coming there. How many substituents and where they are located, both of these are going to affect the nature of the chromophore, and as a consequence are going to affect the position of the wavelength maxima in the spectrum over there. Okay, I think it's time that we wind up for the for this part of the session. We'll try to take a small break over there, and before that, let me just wind up. Let's just try to conclude what we've done so far. Is basically we are continuing with our discussion on the effect of different factors on UV visible spectroscopy or spectrum over there, and then we have talked about continued with the effect of conjugation, followed by effect of solvent, and then substituents over there. And in the second part of our session today, we will talk about how do we use these effects together to find out that how can we predict the lambda max for a given molecule based on the structure of it. Thank you.
With this note, thank you, sir. Thank you so very much for giving us this productive session on UV visible spectroscopy. Friends, there is lot more for you. You are just requested to be with us as we are going to be back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on UV visible spectroscopy. This is a broad topic and we are trying to cover it in many sessions and would be covering in forthcoming sessions too. Friends, for the discussion on the topic, we have with us in our studios Professor Sanjeev Kumar. Professor Sanjeev Kumar is a renowned professor of chemistry, and through him we always get in-depth knowledge of chemistry. If you wish to ask questions from Professor Sanjeev Kumar, do call us through our toll-free number. Our number is 1800-110-430. Now I would like to welcome our guest, Professor Sanjeev Kumar, once again. Hello sir, welcome.
Thank you madam, thank you so much. Okay friends, I think let's try to continue. Remember that what we're talking about is that today we have continued with our earlier discussion on the effect of different factors onto the nature of spectrum in the UV visible range there, and then we talked about the effect of conjugation, and then the solvent effect there, and also the effect of substituents there. And then we also made a statement there that all these effects are cumulative, they all work together. And what basically happened is that this whole aspect, that is the different components working together, actually can be made use of in predicting the lambda max values for a given molecule there. That means we are trying to, on the basis of structure of a given molecule, we can predict what is going to be the lambda maximal value for that particular sample there, or in other ways, will it absorb in the UV visible range or not? If yes, what will be the likelihood of that lambda max value there? Okay, so that actually is coming for the fact because that the effects of conjugation, solvent and substituents are additive there, and these contributions for wide variety of molecules have been put together for a variety of classes of molecules there, organic compounds there, and they have been empirically related in terms of what are called as Woodward-Fieser rules there. This is one of the very significant contribution of Woodward and Fieser, who worked painlessly on compiling together all the kind of spectra of the UV spectra or UV visible spectra of wide variety of molecules there, and primarily these rules, Woodward-Fieser rules, were proposed by Woodward and Fieser, as the name suggests, on the basis of their studies on UV spectra of terpenes and steroidal alkenes particularly. That means what they did was they collated together all available spectra of terpenes and steroidal alkenes, and what they found was that some kind of pattern is there in that, and that pattern they have tried to put together I'm sorry. So that kind of a pattern in their lambda max values could be put together in terms of some kind of a set of rules there. And what basically they proposed is that for any kind of a chromophore, say a diene or I'm sorry. For example, we have a diene or enone. For these kind of things, the functionalities over there, we see that if we have got a diene and there are different kind of substituents are coming over there, in what way do they affect? We have seen that effect in the just a short while before. Okay, so what they did is that all this can be worked out in terms of assigning a base value to a chromophore, the basic chromophore, and adding other the effect of substituents and solvents, etc., in terms of their location and the nature onto that base value there. We'll take a lot of examples for this, and we find that on basis of these rules, there's an excellent agreement between the calculated and the observed values. That is, the values which are predicted by these rules and what are actually observed experimentally, they happen to be fairly close to each other. Let's look at the Woodward-Fieser rules for two kind of functionalities we'll talk about. We'll begin with Woodward-Fieser rules for dienes. What basically is done in this case is that is different conjugated dienes are assigned base values as follows there. That means there are three kind of moieties we have. That is, we have got acyclic diene, that means there are two double bonds there which are conjugated and there is no cyclic structure in that. That is, and this has been assigned a base value of about 217 nanometers. Then heteroannular diene, that means a diene which becomes part of two rings over there, and this is assigned a base value of about 214 nanometers. And homoannular dienes have a value of 253 nanometers. That means the diene happens to be part of a given ring over there. So these are the three base values for different types of functionalities. That basically our functional group happens to be, or our basic chromophore happens to be diene. But under what conditions is diene located, whether it is acyclic or heteroannular or homoannular diene there. So there are different base values. We'll be using that as we proceed further. Secondly, that the contribution of substituents, that is very important here. What you find is that this is the kind of substituent we have and there is a corresponding contribution there. That means if there is an extension of conjugation, the contribution is about plus 30. That is what has been worked out on an average. And exocyclic double bonds there give a contribution of plus 5. Alkyl groups or ring residues give a value of again plus 5. OCOCH3, there is no addition over there. Say a kind of an OR group there, plus 5. SR plus 30, and so on and so forth. So what you find is what are the substituents and what is their effect over there. So this has been collated on the basis of the spectra of known molecules over there. So what do we do? What do we do is we start with the lambda max for a given molecule will be given by the base value there, say 217, suppose it happens to be acyclic one there, and then we put together summation of contribution from substituents there. We see what are different substituents. For each one of them, we take the contribution and add them together, and then some contribution of solvents if it is there. Normally, for alkenes, solvents do not affect much there because typically the spectra are taken already in the polar solvents there, and if you add polar solvent, there is no effect over there. Okay, let's try to first understand when we talk about alkyl substituents or ring residue, what do we mean by that? Let's take some examples and understand that. Suppose this is the molecule I'm talking about over there, and in this molecule, this happens to be my chromophore there, that is butadiene, and these two happen to be alkyl substituents over there. That means this is my basic chromophore there. On the basic chromophore, this is one substitution, there is another substituent over there. So there are two alkyl groups are the substituents in this case. In this case, this is a different molecule now. Again, this happens to be my basic kind of a chromophore, and these three are the alkyl substituents over there. That means this is 1 on this, 2 and 3. In this case, what do we have? What do we have here is that this is my basic chromophore, that is butadiene, and then what we have is there are 4 alkyl substituents over there. So we have to see that we have to keep our basic chromophore over there and see what are different substituents over there, and then put the number together, and for each one of them, say in this case there is a contribution of plus 5 there. Suppose there are 4 of them, the contribution will be 20. We'll come to that. Let's take some more examples over there. So in this case, what do we do? In this case, this is the basic chromophore, and now what do we have is, so there are 2 substituents over there, but these 2 substituents happen to be part of a ring here. So they are called as 2 ring residues. So distinguish between ring residue and our alkyl substituent over there. Alkyl substituent will come only if it is an open chain structure. If the substituent happen to be part of a ring, then we call it as a ring residue. So that's a distinction we have to be making here. So in this case, what happens? This is the basic chromophore, and what we got? 1, 2, 3 ring residues over there. In this case, this is the basic chromophore. So we have got 4 things over there. 1, 2, 3, these 3 are ring residues, and this happens to be an alkyl group over there. So there are 3 ring residues and 1 alkyl substituent over there. So we have to understand the distinction between what is the meaning of a alkyl substituent, what is the meaning of a ring residue, and then how do we locate them. Okay, let's go further. Let's go further and understand one more thing over there. What do we mean by endocyclic and exocyclic double bonds over there? Let's look at this. In this case, for this molecule, we find that this is an endocyclic double bond. That means a double bond which happens to be part of a ring over there. Whereas this double bond happens to be exocyclic. Exo means outside. That means this is a ring part over there, and this double bond happens to be out of that ring over there. So this is an exocyclic double bond, because exocyclic double bond adds to the value there. Endocyclic double bonds do not add normally. Okay, so we have to be clear about it. So in this case, this is endocyclic to one ring and exocyclic to other one there. So you see that this double bond over there happens to be part of this ring. This is endocyclic here. It is inside this ring. But for this ring, this happens to be outside. So this particular double bond happens to be endocyclic to this ring, exocyclic to this ring over there. Let's go further. In this case, what do we have? So there are two exocyclic double bonds over there. So this one happens to be exocyclic to this ring, and this happens to be exocyclic to this ring over there. Going further, what happens in this case? This is exocyclic to this ring as well as this ring. So we'll be talking about this will be counted as twice. So it will have a double the effect over there. So it will be equivalent to two exocyclic double bonds over there. Okay. Now, one more thing before we move further is, that is, what is the meaning of acyclic, homoannular and heteroannular. Let's try to distinguish between the three things there. This is typical example of acyclic. We started with that. Thereafter, now what is this one? This is homoannular, because this double bond happens, this is the whole chromophore happens to be part of one ring there. This is homoannular, and this happens to be heteroannular. We talked about that earlier too. Now what about this one? In this case, since the whole chromophore is not within the ring there, neither inside nor outside there. So part of it happens to be outside the ring, part is inside the ring. So this will be acyclic there. So it is not in the part of the ring there. And so is this one. This again happens to be outside the ring. This again will be acyclic. So we have to we should not get confused by seeing a ring over there and calling it as a homoannular or heteroannular. It is not so. Homoannular and heteroannular will be used if and only if the whole chromophore happens to be part of a ring or group of rings over there. Okay, I'm sure that this is understood, because this is very important to understand, because that is what we're going to make use of in trying to use this Woodward Fizzer rules to predict the lambda max value for different molecules there. Let's take some examples now. Let's try to apply this Woodward Fizzer rules there. The first example I'm taking here is simple isoprene over here. In case of isoprene, what do we have? If you look at it here, so this is the basic chromophore we have. So the base value will be 270 nanometers. That's what we saw there. That is for acyclic butadiene or a conjugate double bond over there. We have got a base value of 217 there. And what do we find is, in this case, this is my chromophore there, and this is the only substituent over there. So there is only one alkyl substituent there, and for each alkyl substituent there is a value for addition of 5 there. So 1 into 5 makes it 5 nanometers. 217 is the base value there. The two will add together to give me a calculated value of lambda max to be 222 nanometers. And what you experimentally observe happens to be 220 nanometers, which is fairly close. Okay, so that is the way we make use of Woodward Fizzer rules to predict the lambda max value for a given molecule there. Let's take another example. Hexa-2,4-diene. So this is my chromophore there. The base value is 217. We got one substituent here and one over here. So we have to keep attention onto the basic chromophore, locate that first, then look for the substituents there. The substituent happens to be two of them. There are two alkyl substituents over there. So 2 into 5, the contribution happens to be 10 nanometers. Predicted value or the calculated value happens to be 227 nanometers. Observed also happens to be 227 nanometers there. So you can see that how effectively we can predict the value of lambda max for a given molecule on the basis of Woodward Fizzer rules over there. Let's go further and take yet another example there. This is myrcene. In this case, what do we have? We have, this is the basic chromophore here. Okay, so the base value will be 217 again. It is acyclic one, and this is one alkyl substituent. So this whole thing happens to be the substituent over there, because this double bond is far away from the chromophore. It doesn't contribute to this, it doesn't conjugate with this, so nothing is there. So we have only one alkyl substituent. This whole thing can be taken as one substituent there. So we have, the contribution happens to be just 5 nanometers there, and the predicted value comes to be 222 nanometers. So please don't get confused here again that seeing there's a double bond there. Make sure if you're trying to look into double bond, it should be conjugating with the basic chromophore to be meaningful over there. Okay, so and the observed value for this happens to be 224 nanometers, which is within about 2 nanometers, which is fairly good. Okay, let's go further and take one more example here. So in this case, what do we do? In this case, this is the basic chromophore we have. So the value happens to be 270 nanometers for this part of the molecule, and then on this chromophore we find that this is one substituent there, 2, 3, 4, and these are not substituents, they basically happen to be the ring residues there. So there are ring residues, there are 4 of them. Incidentally, for the ring residue also the contribution happens to be 5 nanometers, so they will add up to give me a value of 20 there. And then we also have exocyclic double bonds over there. You see that this double bond happens to be exocyclic to this ring, and this double bond happens to be exocyclic to this ring there. So this again adds one more contribution, that is about 10 nanometers there, and the value now comes out to be 247 nanometer. That is the calculated value on the basis of Woodward-Fieser's rules there, and the observed value happens to be 247. So you see how effectively we are able to predict the values there. Let's move further and make one more application of this there. Same Woodward-Fieser rules. If you remember that right in the beginning when we talked about UV visible spectroscopy, I'm sorry, we made a mention of the fact that one of the applications of UV visible spectroscopy is to distinguish between closely related molecules, say isomers in this case. So what you find is, in this case there are 2 isomers given over there, and let's try to calculate the lambda max values for each one of them, and we can see that how distinguished they can be easily distinguished over there. So the base value for this one happens to be 240 nanometers, this happens to be 253 nanometers. Why? Because this happens to be part of 2 rings there. This is heteroannular and this happens to be a homoannular system there. So base value becomes fairly different over there. And then if you look at the alkyl substituents or the ring residues, so there happen to be 4 of them in both the cases. In this case, this is 1, 2, this is one substituent over there, 1 ring residue, and then this is another ring residue, and this is another ring residue. The 3 of the ring residues and 1 alkyl substituent. Again, contribution happens to be 20, and then we also have got exocyclic double bonds over there, 1 of them. Say this one happens to be exocyclic to this ring there, and in this case this happens to be exocyclic to this ring over there. So again contribution of 5, and if you calculate the value now, this will give me 239 nanometers there, this will give me 278. And what I do is I actually take the molecule, run the spectrum and see what is the lambda max. So I can say if it happens to be close to about 240 or so, we say it is this molecule. If it happens to be close to 280, we say it is this molecule. So that is how we can distinguish between isomers of a similar nature on the basis of UV visible spectroscopy there, and primarily making use of Woodward-Fieser rules for dienes there. Okay, you just see that the value happened to be 238 in this case and 273 over there. Okay, let's move further and move to second class of functional groups over there, second class of chromophore, and they happen to be enones. Enones means there is a ketone which is conjugated with an ene over there. Okay, and here again, like in the previous case, what do we have? We have got base values depending on what kind of enone we are having. Okay, so we have got acyclic one there, the base value is about 250 nanometers there. 6-membered ring as the parent enone there, so you see that this is a 6-membered ring over there, and this happens to be part of it, again 250 nanometers. 5-membered ring happens to be parent enone, like this over there, 202 is the value there, and acyclic dienones there, the value happens to be 245, because in this case there is a conjugation coming in there. Okay, so that is about the base values there. And if you go further and look for the substituents over there, this is more involved than in case of dienes there. So what you see is that in case of enones, the contribution of the substituent happens to be very, very significant. Now what you see is the first and foremost is the same one as in the previous case, that is extension of conjugation, again 30 nanometers as before. But alkylic groups or ring residues, now it will depend on at what position they are on the chromophore, alpha, beta, gamma and higher. For alpha it is 10, for beta it is 12, for gamma and higher it happens to be 18 nanometers. So here again, in the previous case what we had was we just counted the number of substituents or the ring residues and multiplied 5, everything was in order. But now we have to be very careful here. We have to see how many substituents are there, how many alkyl groups are there, how many ring residues are there, and where they are located, because accordingly the contribution will be taken care of. Say for an OH group there, at alpha position is 35, which is fairly large. For beta position it happens to be 30. For gamma and higher position it happens to be what, 18 nanometers, and so on and so forth. These tables are available in all spectroscopic textbooks over there, so I don't have to read it out over there. So basically the point I want to bring home here is that is, in case of enones, the effect of substituents will depend on how many of them are there and where they are located. So both of things are to be taken care of. Okay, now as regards the solvent correction again we find, because what happens is most of the enones actually the spectra of them were taken in ethanol or methanol. So that's why since the base value happens to be ethanol or methanol, so there is no volume, there is no correction for the solvent ethanol or methanol there. But suppose we start have a molecule in ethanol or methanol, and then we try to see what will be the value in case of water as a solvent. We have to add 8 over there. So for chloroform it is -1, dioxane -5, and so on and so forth. That means the effect of solvent has to be considered in this case, whereas in the previous case we didn't do much about the effect of solvent because they do not affect significantly there. Okay, so how do I compute the lambda max values here? So there what you do is we start with the base value and look for the contribution of substituents. Since the basic values happen to be in ethanol methanol, so we do not use it as we do not do any addition over there. We just take them values as they are, and then to this we add some kind of a correction for the solvent there. So this part of the formula happens to be same as before. There is a base value, then sigma, that is summation of contribution from different substituents, and then of course we got a solvent correction. We had that in the previous case also, but this happened to be insignificant, so we didn't consider that there. So in this case this becomes significant and we have to consider it. I'll give you one example for that too. Okay, so what we do is the expected lambda max value what we calculate is for ethanol, and then we apply for the solvent correction there. So that is how do we go. Let's take an examples over here. First one, say acetyl oxide. This is the molecule over there. So in this case what do we have? So this is carbonyl group there, this is ene. So this is my basic chromophore enone, and on this there are substituents over there. So the base value, since it happens to be acyclic one, base value happens to be 215, and there are 2 beta alkyl substituents there. Now we have to see, it's important here. So this is a carbonyl group there, this is a double bond over there, ene part of it. So this is my alpha carbon, this is beta 1 there. So on alpha there is no substitution there, on beta there are 2 alkyl groups there, 2 CH3 groups are there. So 2 beta alkyl substituents, and for beta we know the contribution happens to be plus 12. So 2 into 12 happens to be 24, and the calculated value will now come out to be 239, and observed value happens to be 237. Okay, second example, for this case what do I have? The base value now happens to be 215, because this happens to be part of a 6-membered cyclic ring over there, and there is only, because this is the chromophore there, so this is my alpha position, this is the beta position. On beta position there is 1 alkyl substituent over there, so value is 12 here, and there is at beta itself there is a ring residue, so again 12 over there, and we find that value comes out to be 239 nanometers there. Observed happens to be 238, which is fairly close. Now yet another example here. So in this case what do I have? The base value is again 215. Then there is, now you see that this is the alpha position, this is the beta position. On alpha there is 1 alkyl substituent there, on beta there is 1 ring residue there. So 1 alpha alkyl substitution value is 10 now. In case of beta it was 12, so that gives me 10 nanometers. 1 beta ring residue, it gives me 12 again. They add up together to give me 237. And let's go further and take one more example here. So in this case what do I have? The base value for 6-membered ring happens to 215, ring residue gives me 10, beta gives me 12, and then lambda max comes out to be 237. There are repetitive similar kind of molecules over there, but what you find is that we have to firstly locate the basic chromophore and then look for the substituents, the position and the nature both, and then you compute these values over there. Okay, let me take this more example there. say base value happens to 215 again. In this case, you find that this is the basic chromophore there, this is extension of conjugation here, and second one also. So this is an interesting example there. So they will add up to about 60 nanometers over there, because there are 2 into 30 for each extension of conjugation. Then one beta ring residue, again 12, and this is very interesting here, that is homoannular diene system, because extension of conjugation was 1, but now this extended conjugation happens to be part of a ring. So that's why there is addition of 39 nanometers more, and that actually, then there are 3 more alkyl groups there, that makes it 54, and then one exocyclic double bond makes it 5. You can see that this is exocyclic double bond over there. So the value comes out to be 385 nanometers. So you see that how many factors we have to bring in to compute the value of lambda max, which is expected over there. And observed value happens to be 388, which is fairly close to the calculated value there. Now this is one of the last examples I want to take up now, which is very interesting, because in this case I want to compute the value in hexane. What do I do? Base value is 202, beta alkyl group, extension of conjugation 30, gamma residue 18, and then delta residue again 18, exocyclic double bond 5. So what happens is, if I do all this contribution as I have been doing it, I'm quickly running through that, and what I find is the lambda max value comes out to be 285 nanometers. But now, since I want to compute it in hexane, what do? I have to do solvent correction, and that is minus 11 nanometer. The value comes out to be 274 nanometers, which is close to the observed value over there. Okay, I think it's time to wind up for the day. But basically, we have done is, we have tried to put together our understanding of UV visible spectroscopy in a qualitative way. So far, we defined UV visible spectroscopy, talked about the factors affecting spectrum, and then how can we use these factors affecting the nature of spectrum in terms of qualitative determination of the lambda max values there, in terms of Woodward-Fisher rule there. In the next session, we will talk about the quantitative aspect of UV visible spectroscopy. Thank you.
With this note, thank you, sir. Thank you so much for giving us this session on UV visible spectroscopy. Dear friends, as said by Professor Sanjeev Kumar himself, that we would be talking more on the following topic in our forthcoming sessions. So you are requested to keep us watching regularly. Today we are taking your leave with the promise that we are going to meet. Yes, of course, you can write to us at info.cec@nic.in. This is the ID where you can post your questions as well as your feedbacks too. We are taking your leave with the promise we are going to meet soon. Till then, take care. Goodbye. Thank you, sir.
Thank you so much, ma'am.